Okay, hello and welcome back to Chemistry Talk. Today we'll be finishing our discussion of thermochemistry in my series of videos. We've talked about many things in thermochemistry so far. We talked about specific heat, enthalpy, calorimeter problems, and we conquered the phase change problems, which are probably one of the harder ones. But today we'll be discussing how to write a thermochemical equation, our last topic in my thermochemistry series. So what is a thermochemical equation? Well, first you have to have an equation that's balanced. You include the states of the products and the reactants, so that would be, whether it's a liquid or a gas. You also include the delta H value. That's what makes it the thermochemical equation. Do be careful though. Notice when I wrote this chemical equation in words, I said 136.6 kilocalories of energy is absorbed when 2 moles of liquid water is decomposed into 2 moles of hydrogen gas and 1 mole of oxygen gas. The key word here is absorbed. That tells us that Q is going to be positive because absorbed means an endothermic reaction. We're absorbing heat, we're taking heat from the surroundings, so we have a net gain of heat. That's why Q is positive. However, Q is positive. However, if it said released, some amount of heat, some kilojoules of heat, that means the reaction's exothermic. There's a net loss of heat because we released heat, and that would make Q negative. So pay attention to the wording, that's key. All right, first problem, I have 3 examples today. My first example says when 1 mole of liquid methanol is burned, carbon dioxide gas, liquid water, and 726.4 kilojoules of heat is released. Key word there. So I'm going to already write that I know that this reaction is exothermic because we're releasing heat, which means that my delta H in the thermochemical equation has to be negative. Q is negative. So here I'm given a value for Q. When 1 mole of liquid methanol is burned, this amount of heat is released. However, looking at the balanced chemical equation, which you need for a thermochemical equation, that's right here, I can see when it's balanced, 2 moles of liquid ethanol is burned, which means that I need to multiply this enthalpy by 2 to write it the thermochemical equation. So let's do that. Let's write the thermochemical equation. So I have 2 moles of methanol. That's kind of far away. I have 2 moles of methanol. And remember, you must include the states. So that's a liquid. Plus 3 moles of oxygen gas. Got to include gas. Give us, so it's a combustion reaction, 2 moles of carbon dioxide gas and 4 moles of liquid water. But we're not done. I just rewrote the equation from up above. I need to put in my value for delta H to make this a thermochemical equation. But we need to find what that value is. First thing that we got to make sure is that Q is negative. We're releasing heat. So I'm going to find my delta H up here. So for 1 mole of methanol, for 1 mole of methanol, negative 726.4 kilojoules of heat are released. However, in the balanced chemical equation, we have 2. So we need to multiply this value by 2. So my delta H equals negative 1,452.8 kilojoules of heat. So that will go in my thermochemical equation. Delta H is equal to negative 1,452.8 kilojoules. And this is the proper thermochemical equation. We have a balanced equation, states of matter, and the proper delta H. Perfect. Next question. How much heat will be released when 100 mils of methanol is burned? And I gave you the density. So first thing is I need to get the milliliters of methanol into grams using the density. Density is a conversion factor. So 1 mil of methanol weighs 0.79 grams. Now I have grams of methanol. Now I need to get this methanol into moles so I can use my balanced chemical equation. 1 mole of methanol, let's see, carbon is 12, hydrogen 4, oxygen 16. So that weighs 32 grams, 1 mole of methanol. And now I can use my balanced chemical equation to give me heat. So the heat released is going to go on top, negative 1,452.8 kilojoules of heat is released, but not for 1 mole of methanol, for 2 per 2 moles of methanol. So I get an answer of negative 1,793.3 kilojoules of heat. And that's my answer. Notice once again that I used 2 moles here. That's how much heat's released for 2 moles, not 1 mole. Okay, how much energy must be supplied to electrolyze enough sodium chloride to produce this amount of sodium by the reaction? So Q is positive here, heat's positive, so it's an endothermic reaction. So my answer should be positive because it's an endothermic reaction. This is not too bad. I'm just converting grams of sodium into energy. So 64.3 grams of sodium. That's what I'm starting with. I know from the periodic table that 1 mole of sodium weighs approximately 23 grams. And I know from the balanced chemical equation that I want to know how much electrolyzed sodium chloride. So 2 moles of sodium chloride absorbs 196 kilocalories of heat. The grams cancel, the moles cancel, and I'm left with heat. So my final answer, 274 kilocalories. Notice that the answer is positive because it's an endothermic reaction. Q should be positive. Okay. Now, this is probably one of the harder questions you can get. So we moved up in difficulty. So my last example here says that 1.32 grams of sucrose, and that's the sugar that you bake with and you eat, is burned in a calorimeter. The heat capacity of the calorimeter is 9.43 kilojoules per degree centigrade, and the temperature changes from 25 degrees Celsius to 27.3 degrees Celsius. I'm asking for the heat combustion of sucrose. Please note that the heat of combustion is the reaction when 1 mole of a substance is burned in excess oxygen, because combustion, you have some gas here plus oxygen, and you get carbon dioxide and water. That is a combustion reaction. So here we're combusting sucrose, so it won't be a gas, it will actually be sucrose, which is a solid. So in this case, it's sucrose. So the heat of combustion is for 1 mole. So I'm going to be first look for the heat of combustion for 1.32 grams. Now, how do we find the heat of the calorimeter? Well, in this case, in this calorimetry problem, we have two things. We have the sucrose, and we have the calorimeter. No liquid here. What do we know? Well, we know the sucrose is 1.32 grams, and I'm looking for the heat of combustion. What do I know about the calorimeter? I know the calorimeter constant, 9.43 kilojoules per degree centigrade. I know the initial temperature of everything is 25 degrees Celsius. The final temperature of the mixture, 27.3 degrees centigrade. Delta T for the sucrose in the calorimeter, 2.3 degrees centigrade. So what I need to do first is find the heat of the calorimeter. The heat of the calorimeter always equals the calorimeter constant, Kc, times delta T. What's the calorimeter constant here? Calorimeter constant's 9.43 given. What's delta T? We just calculated that, 2.3. Heat of the calorimeter, 21.7 kilojoules. Should be two significant figures, but we'll assume that that was 2.3. Okay, so that's the heat of the calorimeter. Well, what do we know about the heat of sucrose? The heat of sucrose plus the heat of the calorimeter, using the law of energy conservation, equals 0. So the heat of sucrose is the opposite sign of the heat of the calorimeter. So the heat of sucrose is negative 21.7 kilojoules. But we're not done. We're looking for the heat of combustion. That's per mole of sucrose. This is per 1.32 grams of sucrose. So I know that negative 21.7 kilojoules of heat is released for 1.32 grams of sucrose. I need it per mole. So per 1 mole of sucrose, we have 342 grams. That's the molar mass. Grams cancel, and you're left with kilojoules per mole. So your answer, with the proper amount of significant figures, which is 3, is negative 5.62 times 10 to the third kilojoules per mole. So that's what the heat of combustion is. And that is your answer. I hope this series of videos helped you to understand thermochemistry. Comment any questions you have, and soon I'll be starting another series of lectures. Thank you very much.